So I'm just going to work out more problems in this video. But last time we derived this equation. We said this is quite helpful right here. It relates two conserved quantities right here. So when we write energy and momentum equations out, here's at least something that relates the two of them. And let me just rewrite it right here. E. If I just take the square root of both sides, it's the square root of p squared c squared plus m squared c to the fourth. Now, if you're at rest, if u is equal to 0, then you have no momentum. So that's 0, and E is just the square root of this, which is just mc squared. E is equal to mc squared. Now, if m is equal to 0, we'll have particles that have 0 mass right here. And if m is equal to 0, then it looks like you just take the square root of that. That's just Pc. E is equal to just Pc. Okay, so, and if neither one are 0, then you have both. Okay, so now, continuing on with that problems in that survey book, again, you can get these problems off of the canvas under files. And if I go down to number 21, now they say an electron, so here we have an electron right there, has a kinetic energy of 1 MeV. So it's moving, it has a kinetic energy of 1 MeV. And it makes a head-on collision with a positron at rest. Positron is just like an electron, but it's a plus charge. I'll go over those at some later time, probably the next lecture. But it's just the antimatter particle of the electron. And when matter and antimatter come together, it gives you all energy, which is light. And so what comes out of here is, in the collision, two particles annihilate each other and are replaced by two gamma rays, which are two light particles, of equal energy, each going off at an angle, equal angle theta. So when this thing hits, what comes off, I'm going to draw it like that, even though they're really, we can think of them as particles. They're going to go off at equal angles, theta and theta. And here's your two gamma rays, gamma and a gamma. So those are the two particles of light. Light has no mass, so we can say this is the relationship between the energy and the momentum for the gamma rays right here. Okay, so this has a certain, let me call this energy E sub E, and has a certain amount of momentum, and these have a momentum too. Now, this looks like a problem that you do in classical mechanics. Again, it's a two-dimensional collision, so you just use momentum, but you have to do the momentum. Well, let's look at the momentum in the x direction, momentum in the x, in that direction. Well, we got the momentum of the electron, whatever he has no momentum, he's at rest. Then afterwards, all you have is the momentum of this gamma, but you just have the x component of it, so it would be momentum of the gamma cosine theta plus the momentum of this cosine theta. Since the angles are the same, the y components of momentum are the same, which means the p gammas have to be the same, just because they're equal gammas right here. So we just have two of them. There's two of them. That's the total in the x. Matter of fact, we don't have to look at the y components, because this y component, if we look at we'll write it out. Py gamma, py, before it's 0, because nothing's going up and down. Afterwards here, you'd say p of the one going up, gamma sine theta, minus the one going down, p gamma sine theta. Well, I knew P gamma sine theta equals P gamma sine theta, so I didn't even need this right here. Okay, so there's the momentum equation. Then we also have an energy equation. Energy equation. The energy of the whole system before the collision, well, this guy has kinetic of the electron, plus he's got some rest energy, plus m sub e c squared, plus this guy he has no kinetic, but he does have rest energy, plus m, it's got the same mass, these two have the same mass right here, c squared. So there's the total energy before, and afterwards we got the energy of this plus the energy of that, but they both have the same momentum, and we know momentum and energy are related, so they both have the same energy. So this is just 2 times the energy of the gamma. Okay, so what did we want to find out of this right here? That's actually on the next page. It says, find the energy, momentum, and angle of emission of the gamma ray. So what they want is they want E gamma, P gamma, and theta. Those are the 3 things they want right here. Well, it looks like we can get E gamma from right here, because we know the kinetic, that's 1 MeV, that's a half an MeV, that's a half an MeV. So all this is just 2 MeV. So this is just 2 MeV equals 2 E gamma. So each one of those E gammas, just divide out by 2, was 1 MeV. 1 MeV. So this is a 1 MeV gamma, that's a 1 MeV gamma. Now if I wanted to get their momentum, well, heck, I can just come over here because these are light, and light E equals PC. So P is just E divided by C. So P is just E, which is 1 MeV. Well, let's just write it out as E over C. Which is MeV all over C, which was 1 MeV over C. So there's your P and the gamma, it's just 1 MeV over C. And then they also wanted us to get the angle. Well, it looks like we can get, let's see, can we get the angle from right here? Let me see, we know what this is. How do we get P sub, if we knew P sub E, the momentum of this? Well, we could get the momentum of that because we'll come back for the electron up, for this electron, just all by himself. He's got both terms. So this is the energy of that electron. So it's that energy of the electron. We can write it 2 ways. We can write it as the square root of P squared C squared plus mass of the electron squared C to the 4th. Or we could write it as the kinetic plus the rest mass. There's 2 equations for it. So it's also equal to the kinetic, which is 1 MeV, plus the rest mass, which is a half an MeV. Remember we said it's 0.5. Okay, so this will give me the momentum of the electron. So this over here was just 3/2 MeV. Okay, so if we wanted to solve for P sub E, we'll square both sides. So we got P sub E squared C squared plus M sub E squared C to the 4th equals that squared, which is 9/4. That's just a unit, MeV. So I'll just remember this has units of MeV squared. Okay, and then we know what this is. That's a half squared, so this is 1/4. If we take this and bring it on the other side, 9/4 minus 1/4 is 8/4. 8/4 is just 2. So P sub E squared C squared is just 8/4, which is just 2. And then we'll take the square root of both sides. So P sub E C is equal to the square root of 2. I'm not going to put the units in right here. Okay, so now if I want to, I think we can go ahead and we can calculate. What do we want to do? We want to get this angle. So the cosine theta equals P sub B over 2P gamma. So cosine theta is equal to P sub B over 2P gamma. P sub B over 2P gamma. And we just said what P sub B was. Actually, I'm just going to multiply top and bottom by C. Why? Because I have PEC, that's the square root of 2. So this is the square root of 2. And P gamma C, P gamma C. Well, if I just bring the C over here, P gamma C is 1 MeV. So that's 1 MeV. Okay, so I'm just left with the square root of 2 over 2. If the cosine of theta is the square root of 2 over 2, then it looks like theta is just 45 degrees right here. So it looks like this thing's going to be at 45 degrees, and this one is going to be at 45 degrees. Now, I said, well, okay, they didn't ask this, but what if these didn't go off at equal angles right here? What if one went forward and one came back this way? I said, how would things differ? So let's just look at this exactly the same way, but this electron is going forward at 1 MeV. And again, there's my positron. There's my electron. This was the kinetic. Except when they collided and they emitted their photons, one went this way and one went that way. So we'll call this gamma 1, say, and this gamma 2. Okay, so now what would be different? Now this is all one-dimensional, but if we wrote out and this thing has a certain momentum, P gamma 2, they're not going to be equal now. P gamma 1, and this has an energy E gamma 2, and this has an energy E gamma 1. So if we write out the momentum equation first, the momentum of the electron, that has no momentum, and then afterwards you got P gamma 1 going that way, I'm calling that way positive, P gamma 1 minus P gamma 2. Okay, so there's your momentum equation. If I look at my energy equation right here, the energy of this, that has 1 MeV plus his rest mass, that's a half an MeV, plus that rest mass, which is a half an MeV, just like we had before. Remember, the total energy was just 2 MeV. It's right here, it's the same thing we had before, it was just 2 MeV. So the total energy of this is 2 MeV. And now it equals, we don't subtract the energies. Remember, energy is a scalar. This is E gamma 1 plus E gamma 2. Gamma 2. Okay, now if we multiplied, let's multiply everything on this equation by C for a minute. If I multiply this by C, C, and C, you'll notice this is E gamma 1, and this is E gamma 2, because we said for a photon, E is just PC. So this and this are the same, and this are the same. And so you'll notice if I wanted to, so if I just rewrite this equation, this is P sub E C is equal to E gamma 1 minus E gamma 2. What I want to find is the two energies of these two gamma rays right here. Now, if I knew this number right here, then I could get it, because if I add the two equations, this term drops out, this doubles. If I subtract the two equations, then this term subtracts out and this doubles. If I only knew this, PEC. So how can I get PEC right here? Well, what I can do is do exactly what we did before. PEC is exactly what it was before. It was 2. We haven't changed the initially what it's coming in. Actually, it's right here. It's just the square root of 2. right there. So we haven't changed this. The only thing we're changing is what's happening over on this side. So this is just the square root of 2. So we got the square root of 2 equals E gamma 1 minus E gamma 2. So now let's just say we add these two equations. If we add these two equations, we get, this is MEV. If you add these, you just get 2 plus the square root of 2. And if we add the right-hand side, these are gone, and you get 2 of these, 2E gamma 1. So we got E gamma 1 is equal to 2 plus the square root of 2 all over 2. And that's in MEV. Well, what would that be? That's, if you distribute this through, that's 1 plus the square root of 2 over 2. And if you remember, that's like the cosine of 45, which is 0.7, plus 1, that's like 1.7 MeV. And then if I wanted to get the other one, I would just subtract the two equations. If I subtract, take this one and subtract off that one, 2 minus the square root of 2. If I subtract them, the E gamma 1s are gone. You subtract these two, and you get 2 E gamma 2. Divide that out, and so you get E gamma 2 is equal to 2 minus the square root of 2 all over 2, which is like 1 minus 0.7, 1 minus 0.7, which is like 0.3 MeV. Okay, so E gamma 1, you can see that this one's got to carry most of the momentum. Why? Because this thing was going this way to begin with. This one has to have more momentum than that one. Okay, this one has 0.3 and this one had 1.7. Okay, so again, we're just, you notice we're not even touching velocity unless they really ask for it. I'm not going to go near it right there. So if we now look at number 23, they say an unstable particle of mass, and they give us the mass. I'm just going to call it M, but they give it to us right there. Is initially at rest. Okay, and then it disintegrates right here, and it flies off into two fragments. Two pieces go flying. They have to be back to back to conserve momentum. One of them is going to take off at U equals 0.987 c. That's the speed of that one. And the speed of this one is, say, 0.868 c. Okay. And they just want to find what is the mass of these two fragments. Okay, well, again, we write out, again, the momentum, except now they give us U's here. But let's go ahead and write out the momentum equation. The momentum equation, this has 0 momentum. It's not moving. Let me call this one momentum 1, and we'll call this one the momentum 2. So it's momentum 1 minus momentum 2. Okay, and then we might as well write out the energy equation. The energy of this is just, it's not moving, so it's just mc squared. Afterwards, we have the momentum of this, the energy of this. Now, which equation, since they gave me the U, the energy of that right there, the total energy of just this one particle, I guess we can just use this equation right here. Since they gave me U right there, the only thing I don't know is the mass of it. So we're going to just use that equation. So this would be, for this one, it'd be M, we'll call this M1, that's what they want, and they want M2. It'd be M1 c squared all over the square root of 1 minus this number squared, 0.987 squared. The c squares are gone. Plus the energy of this one, which would be M2 2c squared all over the square root of 1 minus 0.868 squared. Okay, and well, let me come back up to this equation and plug in our momentum. Since they've given me u, I might as well plug them in. And that means P1 equals P2 from this equation. But P1, the momentum of that one is just M1u all over the square root. Remember what u was. M1u, which is 0.987, all over the square root of 1 minus this squared, which looks exactly like that. 1 minus 0.987 squared. And that equals the momentum of 2, which is M2 times 0.868. C, 868C, divided by the square root of 1 minus 0.868 squared. Okay, so now we have this equation and we have this equation, and we only have two unknowns. We know m, they gave me m, and I know everything else, so it looks like all I have to do is say solve for m1 and 1 and plug it into the other, right there. Okay, I don't even know if I want to do that because then it's just algebra going through here. But you noticed if I do solve for solve for m2 out of this equation, you get m2 equals, we've got this, which is m1.987 C, we're solving for m2. You got this times the square root of 1 minus 0.868 squared. And then what comes down below, we have this term, square root of 1 minus 0.987 squared. And then we also have this number coming down, which is 0.868C. Okay, and then if you went and if you plugged it into here, now you'd only have one unknown, which is m1. And you'll notice that this term and that term would cancel. And then this would still be a common denominator because now you'd have both of these two in there. Well, okay, we'll do it. So now we have mc squared. Actually, there's a c squared in every term, so let's just cancel those. So we got m equals m1 over this, square root 1 minus 0.987 squared, plus, now we're going to plug in m2 here, and that term cancel. So we still get an m1, we got the rest of this stuff right here. So we got m1 0.987c divided by square root of 1 minus 0.987 squared times 0.868c. Okay, and again, we're trying to solve for m1. I can throw this common denominator and put it up here. So we got m times the square root of 1 minus 0.987 squared. And then on this side, if I factor out the m1, we get 1 plus this ratio. The c's are gone. 1 plus 0.987 all over 0.868. And then just bring this down below, right there. And when you do that, you end up with M1 is just 0.07. It's only 7% of what this one right here is only 7% of the one mass. And if you then go ahead and once you know M1, you can solve for M2. M2 was just 0.26 M. You notice M1 plus M2 does not add up to M right here. A lot of that mass went into this energy right here, and so that's why the sum of the two don't add up. Okay, so there is, again, on all these, what am I looking at? I'm looking at writing out the momentum equation, and then I'm writing out the energy equation. If they don't give me U and they don't ask for it, I probably won't use an equation with U. If they do, I probably will. Okay.